Okay. I know some of you guys are having problems with the calculus. I found a little website that does derivatives for you. So I just did an example, this one, right? It'll be 3x divided by x squared plus 1. And here's a website. It's called www.derivativecalculator.net. I'm sorry, there's a dash between derivative and calculator. www.derivative-calculator.net. So I did one of the quotient rules. I think that's one of the hardest. You don't have to do this. This is just for you guys who have any phones. And like I said, I will do. You won't get a product rule or quotient rule on test. So 3x divided by x squared, and in this thing, it has a little stuff here that tells you what it is, right? To do something to an exponent, you do the little caret top that's above the 5, above the 6 on most keyboards. 3x divided by x caret top 2, which means x squared, plus 1. And it looks just like this, just like the problem on the practice exercise. The problem on the practice exercise is right here. And once you do that, just hit go, and it'll calculate the derivative for you. So the first derivative here is 3 x squared plus 1 minus 6x squared divided by x squared plus 1 squared. Now, the great thing about this, I mean, you can simplify the answers, but you can show the steps. So you go down here to show steps. You have to go down. And here it is. They take the derivative of the denominator times the derivative of the numerator minus the minus the numerator, and they put 3 out here, times the derivative of the denominator. So first they do with the denominator, they do this, so we end up with 3x squared minus 2x plus 0, x plus 1 over x squared plus 2 squared, and that equals 3, 1 minus x squared plus 1 over squared. Now you could have left it like that. The alternative result the alternative result before they simplified is this. So, okay. Like I said, you don't have to do this. It's just those of you who are having trouble with calculus. It'll do simple derivatives. It'll do more complicated ones. So, I just wanted to show you that it can do a complicated one. Okay. Questions? This is the first homework, first homework question on the assignments, and we covered this yesterday. Suppose the demand for home heating oil in Connecticut is given by Q equals 20 minus P HHO plus 0.05 price of natural gas minus the temperature. And the temperature, well, let's do the definitions. Q is the quantity of home heating oil. PHH0 is the price of home heating oil. PNG is the price of natural gas per unit. Temperature is the absolute difference between the average winter temperature over the past 10 years and the current winter temperature. So if the current price of home heating oil is $1.20, the current price of natural gas is $2, and this year it's 40 degrees compared to 28 degrees, so therefore on average it's 12 degrees above the average, right? What's the quantity of home heating oil demanded? So basically all we have to do is plug. So I have Q is equal to 20 minus 2, and what's the price of home heating oil? $1.20 plus 0.5. Price of natural gas is $2. And finally, the difference between this year's temperature and other year's temperature is 12. So,
We would sum 12.
I'm sorry?
It's minus temperature, then we would sum the 12 here.
Ooh, thank you. Minus.
It's a little bit, I guess, confusing for me because the temperature is higher right now.
Oh, yes, the temperature is higher.
So that would mean that theoretically, at least there should be.
Theoretically,
heating
you're right. Theoretically, at least to my logic, that would mean we're going to use less home heating oil.
Yeah.
But for some reason,
This is absolute.
they use the absolute value of temperature. Okay, so I have 20 minus 2.4 plus 1 minus 12.
$6.6.
Okay, 6.6. How much, and the second part of the question is how much did the change in winter temperature affect the demand in comparison to the average winter temperature? And of course, that's 12. I'm sorry? Budget? Okay.
It lowered it, right?
Yeah, it lowered it, even though it's above it, even though it's above,
Well, it lowered
it
the
lowered it,
demand.
but if it was colder, it would still lower it. So that's what I don't.
It's absolutely, yeah, that's the problem. It shouldn't be
Okay,
absolutely.
but it's something that's this question I'm almost sure I got from the book. So it's something they did. It doesn't have to make logical sense, at least that part. But the important thing is B, what's the estimated price elasticity of demand of home heating oil? Now, remember last week I told you I could give you two things. I could give you a formula, or I can give you the percentage change, the percentage change in the two variables, in this case, quantity demanded and price. What am I giving you here? I'm sorry?
The formula?
Formula. Okay. So how do we do it when I have the formula?
You have to look for the equivalent equation.
Well, just use this equation. In fact, you don't even have to put the numbers in here. Well, actually, you just, never mind. So what's the first thing we need? Or what do we need in general?
this price elasticity.
Price elasticity.
I need the chain of Q divided by the chain of P.
Okay, how do we get that from that formula?
Chain of 20. I have Q. I have P. I have to do the formula.
Okay, what do you have to do with the formula? Somebody help me out here. What do I do? What's the first thing I do with the formula? You told me the change in Q over the change in P. What's another way we can do that? When we have, let's say we have, instead of the big changes, we have infinitesimal partial changes, holding everything else
Factor
fixed.
it,
Was that?
we just, we do the factor, dx. I mean the partial.
The partial.
The partial, sorry, not factor, the partial.
What's the partial of price with respect to Q? So I heard somebody say it was a female voice. Where'd it come from? Was it you? Two? Perfect. Actually, it's -2, but that's okay. -2 is the derivative of the price of home heating oil with respect to Q. So, I have the partial of Q with respect to P times P over Q gives me -2 times P over Q. Okay. So the partial right here is -2. What's the price of home heating oil? Can you see a little cursor? I'm putting it right above the price of home heating oil. What is it? $1.20. Perfect. And what was the Q we calculated a second ago? I hope you guys wrote it down because I erased it.
6.6.
6.6. Perfect. So -2 and 1.2 over 6.6. And help me out here. Well, it's 2.4 over 6.6. That's not 1/3. Somebody help me out with the calculator.
Here, I'll do it.
36, 36.
I'm sorry?
36, 36.
Everybody get that? And of course, this is negative. But I wanted an absolute value. Okay, so the next question is, if the seller of home heating oil are profit maximizers, how should price be adjusted? If I want to increase revenue. Is demand elastic or inelastic? No play with it? Too small?
Let's see.
Okay, sorry. I didn't want to turn on this light because it fades out the thing, especially the way it's flickering. Point 3636. Any less, please? Actually, let me put a 0 out here, so the the absolute value doesn't look like a one.
Inelastic.
Inelastic. Okay. So what should the seller of home heating oil do? Raise the price.
It's inelastic because it's less than one, right?
Less than one. In absolute value.
Okay, yeah. Less than one.
And this is why they are supposed to raise the price.
Because it's inelastic, yes. And when you raise price when it's inelastic, you get an increase in revenue. If you raise quantity when it's inelastic, you get a decrease in revenue. Okay. Questions? Okay. So we're gonna do, demand estimation today. So let's start. The first thing we need to worry about is something called an identification problem. For our purposes, a problem incurred by including the independent variables, that's stuff that affects demand, that do not affect the dependent variables, that is demand, or excluding independent variables that are relevant. So my first problem is including those variables that affect demand. Leaving out those that don't affect demand, right? And making sure I don't leave out any variable that does affect demand. So it's difficult to estimate all the variables that may affect demand. That's just logical. In addition, right, the interaction of demand and supply can be stored in the estimate, right? We basically have to do these two things simultaneously. So here, it looks like, right, supply is increasing. And with that supply increasing, we have lower prices. Over here, I have both demand and supply shifting. And that gives me the same effect in terms of prices. And the question is, how do I differentiate between the two, right? If I don't know what supply and demand is, right? Or if my estimates aren't accurate. So the simultaneous relationship, and there's a definition, concurrent association, right? In our example, supply and demand determines price and quantity of the product simultaneously. So it makes our identification even harder than just estimating either demand or supply, since you have to do them both at once. We have to deal with all the factors that affect supply, all the factors that affect demand, and any one that might affect both. So how do we do that? Well, we always start with a theoretical or a logical basis, right, to figure out where we start. Once we have that, we can start with interviews or experimental methods. The customer interview, questioning customers to estimate the demand relationship. You ask them, if I increase price, would you buy it? And you ask that in different ways to try to get the best answer you can. The problem is that many times customers are simply unable because you really haven't thought about it. If you're in the store and you're going to buy, you make that decision, but in front of a surveyor, your decision might be different. So they're many times unable or unwilling to answer correctly. Not only that, but if you don't want the price to increase, right? If you don't want these guys to increase price, you're going to tell them, hey, I'm not going to buy that if you increase price. But it's one way. Like I said, if you ask the question in different ways, you might be able to get a better answer, but you still have problems. So a market experiment might be a better option. For a long time, there was a saying in marketing, see how it plays in Peoria. It was a city in Illinois called Peoria. And it basically had the average of everything in the US. The average was 2.4 children, right? 2 cars, a dog, etc. Basically, it was basically a small example of the entire US. So basically, they used it as a test market. So the supermarket was filled with all kinds of test products, right? So basically, what they do is manipulate prices in that market, right? And see how demand was affected. Okay? This way you can see how customers actually respond to changes in the variables. And it might not just be price, it might be price of other goods, related, either substitutes or complements. The problem is that you can't control everything that's going on. Somebody else might change the price of a substitute or, excuse me, or a complement. There might be a sale in the next town over, and some people might go to that sale. Not only that, but you can't control the economy. People are losing their job or getting raises. You can't really control those things, and it's hard to estimate. So that's a problem with market experimentation. The other way to do this is in a lab. You can do this with animals, but it really doesn't get you a lot because you're really looking for demand for humans, right? When we did our indifference curves, they do this with rats. They change the price of pellets of 2 different pellets. The rats go and they press a lever and they get the pellets. There's a price change, right? They press different levers at a different amount of time, and they were able to get basically indifference curves for the rats. But when we have humans know that eventually you're going to leave this experiment. So the way you perform with that fake money that they give you, and the way you perform with real money that you earn might be different. So, like I said, one problem with this type of study is participants are likely to act differently in the experiment than they would in the real world. Another problem is that these things are extremely costly. Using both these methods, right, or all 3 of the methods, we can estimate point and arc elasticity. I can also measure cross elasticity. We, however, be aware of the limitations to estimating demand in these manners. Okay. So once we get the data, right, how are we going to analyze it? Probably the most common way is with regression analysis. Okay? It's a statistical technique that describes the relationship among dependent variables. Right? In other words, it describes how one variable is related to another. In multiple variable regression analysis, it describes the relationship of 2 variables holding any other variable that might affect demand, or in this case, also supply, fixed, just like we do when we're analyzing, or when we take our partial derivatives, we're holding everything else fixed. Okay. Now that brings us to the following: whether this is a deterministic relationship, an association that's known with certainty, or a statistical relationship, which is an imprecise link between 2 variables. Okay? So we're going to get to whether this constitutes causation or simply correlation. All right? So correlation is a statistical relationship between 2 variables. It, however, doesn't tell us if one variable causes movement in the other, just if they move together, whether it be positively or negatively. But it doesn't tell us, right, if there's a causal effect, if one variable affects the other. Because it's difficult to differentiate between correlation and causation, we have to be very careful in choosing which variables we include in our regression. We have to have some theoretical or logical basis for including the variables in our regression. If you don't, well, then you're more likely to get correlated variables that don't have a causal effect between the independent and the dependent variable. And in this case, for demand and supply, our dependent variable would be quantity. I give some examples now. A stork is, I know there's a word in Spanish and I forget it. Basically, it's that bird that brings babies, right? Dylan?
That's a win.
At one time, right, there was a positive correlation between the amount of babies born in Norway and storks, right? So a researcher might conclude that storks actually deliver babies. We know that's not true, but it brings a point home. Another problem might be a third variable that's causing the effect, right? I like this one because, well, it reminds me of something. So basically, you see your mom or the kid sees his mom getting on the scale and getting upset because she can't lose weight. So it makes her cry. The kid falsely assumes that stepping on the scale is what makes her cry, when it's the fact that she can't lose weight. So there's a third variable, in this case, weight loss, that causes the effect. And stepping on the scale and crying are just a statistical relationship. Okay. I can also have reverse causation, right? In other words, instead of some variable that affects quantity, right? In this case, I can have quantity, or the quantity demanded or the quantity supplied, affecting the independent variable, right? So that's reverse causation. And this is an old one. I think I'm going to eliminate this one. But basically, my niece, one time, I was sitting in the next room and they were playing, and the kids were getting on my sister's exercise machine. And my niece got mad at them and told them not to use the exercise machine because it would cause them to be fat. Again, this is an example of reverse causation. My sister was using the exercise machine to lose weight, whereas my niece thought that because you were fat or because you use the exercise machine, you got fat. Again, reverse causation. Okay. In both examples, right? The one on the scale and my niece, the conclusion was wrong. In the first example, also correlation between the number of storks and the number of newborn humans with no causation. We know that. In the last example, the kids concluded the correlation between exercise and body fat meant that exercise contributed to body fat, and the true causation was reversed. Okay. Questions? Are you sure you guys don't have questions? I'm going really fast. Okay. In general, we analyze data. There's three types of data. Right? These include time series and cross-sectional data, and a combination of the two called panel data. Time series is where you measure one variable across time. Cross-sectional data is where you analyze many variables in one time period. And of course, panel data is a combination of the two. We have a bunch of data over many time periods. So our time series data, a periodic sequence of economic data. It usually tracks one data point over time, right? Cross-sectional data, a sample of data taken at a given point in time, and it has many data points across that time period. And finally, panel data that has many points within a certain time period as well as across time periods. So basically you have a cross-sectional data repeated many periods. That's panel data. So the simplest way to analyze the sample, right, is with what's called a scatter diagram. A scatter diagram is a plot of data where the dependent variable is plotted against the independent variable. Right? With time series data, you may want to use time as an independent variable because you only have one variable across time. With the scatter diagram, one can usually visually expect the graph to determine if there's a correlation. Okay. So here we have X and Y and a bunch of data points. Right? What do you guys think? What's the relationship? No relationship? You have a question? Okay. No relationship? And I'm sorry?
There's no mechanism.
Okay. I tend to agree, there's no relationship. However, if I eliminated these two data points, it kind of looks like we have a negative, so it might be, but we do have a negative relationship with outliers. Again, right, you'd have to look at the theoretical basis for the two models to see if maybe eliminating these 2 points in the analysis is justified. Okay, here we have time series. I have Y, my dependent variable, and I have time on the horizontal axis. Right? What's the relationship here? There's a positive relationship. Right? As time goes on, Y increases. So how do we specify a regression model? Right? So I picked the variables to be included, and as stated, you can't do that randomly. We have to have some theoretical basis for choosing the variables. Many times the data on variables you choose won't be available. In these cases, you might want to proxy the variable, find something else that might be related to the variable that you want to use, and use that. Or another option is to collect the data, which is, of course, time-consuming and expensive. So here I have an example of a linear regression model. Right? I have Q is equal to an intercept, B0, plus B1, X1, where X1 is something that affects Q, plus B2, X2, where X2 is something that also affects Q. So if I just look at B1, right, it's the amount that Q changes when X1 changes, holding X2 fixed. We also have nonlinear models, right? It can be multiplicative models, nonlinear relationship that involves X variable interactions. For example, a Cobb-Douglas production function that we'll see. We actually saw at one time, just really quickly, a Cobb-Douglas utility function, right? We had Y equals, I'm sorry, U equals X to the alpha, Y to the beta. That's a Cobb-Douglas function. Many times when I have a nonlinear relationship, I can manipulate that. I can manipulate the data to get a linear relationship. For instance, with the Cobb-Douglas, if I take the natural log, right, I'll get a linear relationship with the natural logs. So, getting back to this linear relationship, we have something known as least squares methods. And there's 2 or 3. The most common is known as ordinary least squares, right? It's a method that fits a line that has the smallest total square distance from each data point. So I have to fit a line between all these data points, and the distance between the dot and the line, right, the sum of these distances has to be the smallest possible. So we're not going to go through the math of how to do that, but for most cases, we can do it with a statistical package. Okay. So in the graph above, the line has the smallest total square distance from each data point. So there are really two types of regressions for analysis when you're learning about regression analysis. You start with a simple regression, where you have one dependent variable and one independent variable, right? So the relationship between one dependent variable and an independent variable. And then you move on to multiple regressions. It's a relationship between a dependent variable, which would be a dependent variable, and two or more independent variables. Again, each coefficient in a multiple regression, right, tells you how that variable changes the dependent variable, holding all the other variables fixed, just like our partials. Okay. Questions? So, oops. We're going to look at some of the measures of regression model significance. The first one is known as the standard error of the estimate. Sometimes it's also known as the standard error of the regression, right? That's a standard deviation of the dependent variable after controlling for the influences that all the dependent variables have. I'm sorry, all the independent variables have. So let me say that again. The standard deviation of the dependent variable after controlling for the influences, for the influence of all independent variables. In this case, all the x variables. Right? In other words, this is a measure of how well the regression fits the data. Right? In other words, how close is that line to all the data points? Right? I sum up that distance, right, an absolute value. In this case, we square them and then take the square root of that, and basically gives us absolute value, right? And see how well, right, the data fits our regression. Right? If all the data points fall on the line, the standard error of the estimate is going to be 0. Right? There's no error whatsoever. It's perfect. Right? The further away they are from the line, the bigger the standard error of the estimate will be. So if I have a dependent variable, right, I have my regression line. I can also calculate an upper bound and a lower bound, right, using my standard error of the estimate. Right? I multiply it by its t-statistic times the standard error of the estimate, and it gives me an upper bound and a lower bound. And that t-statistic that we talked about, that is there, or that we haven't talked about, well, I can change that. I can change the number given a different level of confidence. I can say I want to be sure with 95% confidence that the true regression falls between these 2 points, or it can be 90% or 99%. Of course, the bigger the confidence number I want, if I want 99%, the upper bound and lower bound are farther away from the regression line. Okay. So we can confidently say with some level of probability that the true regression in the line will fall between the upper bound and the lower bound. And the level of probability will be determined by the level of our t. Okay. So our next statistics is something are very much related. The first one is our correlation coefficient, right? And basically it's a goodness of fit for a simple regression, right? And in general, the correlation coefficient is going to be between 1 and -1. Not in general, always going to be between 1 and -1. If there's a negative relationship, it'll be negative. If there's a positive relationship, it'll be positive, plus 0. For multiple regressions, multivariable regressions, right? We have something known as the coefficient of determination. Most of the time when you hear people talking about the coefficient of determination, they'll call it R squared. So it's a measure of goodness of fit for a multiple regression model. The square of the coefficient, multiple correlations. So in this case, R squared will never be negative. It'll always be between 0 and 1. And basically it tells you how much of the variation in the dependent variable the regression explains, right? So if it's high, if it's close to 1, it explains a lot. If it's close to 0, it explains almost nothing. Okay. In other words, how much of the variation in the dependent variable is explained by the model, right? So R squared is basically a measure of the variation explained by the regression divided by the total variation as well. The next thing is the corrected coefficient of determination or adjusted R squared. One of the problems with R squared is that if you add variables to a regression model, no matter how bad those new variables are or how very little relationship they have with the dependent variable, it's always going to increase your R squared. Now, it'll increase it for variables that don't affect, it'll increase it by a tiny amount of 0.00001, but it'll always increase it, right? It'll never decrease it. So because of that, they came up with a new estimate that takes into account the degrees of freedom. In other words, just adding variables won't affect the adjusted R squared, because if you add variables that aren't related, your adjusted R squared would actually decrease. And that's basically, so I have R squared minus K. K is the number of variables in your regression, minus 1, divided by N minus K. This is also known as degree of freedom. It's the total number of observations minus the number of variables, K, all multiplied by 1 minus R squared. In other words, 1 minus R squared would be that variation not explained by the regression model. And the degrees of freedom are the number of observations beyond the minimum needed to calculate a given regression. If you remember way back when you took math class, right? If you had, or an algebra class, if you had 2 variables, right, in an equation, you needed at least 2 equations to solve those 2 variables. Right? You needed another variable. If you have 3 variables, you need at least 3. This is basically the same logic. You need at least as many observations as you have variables. And in general, you want many, many more variables. Okay. The next statistic is known as something known as an F statistic. Now, this statistic is related to R squared, and in fact, you can calculate it using R squared, right? So it's a measure of statistical significance for the share of dependent variable variation explained by the regression, right? So it's the explained variation divided by K minus 1, or again, K is the number of variables, divided by the unexplained variation, minus N minus K, where N is the number of observations and K is the number of variables. The whole thing, N minus K, is our degrees of freedom. So our explained variation is essentially R squared. Our unexplained variation is 1 minus R squared. So I can calculate my F statistic, right, using R squared. Now for F statistics, right, depending on what level of confidence you want, you can measure whether it's statistically significant or not, right? Depending on the table, either the computer will spit it out, or you can go to a table that gives you the F distribution and say for this level of confidence and this many degrees of freedom, if my number's above that, it's significant. If it's below that, it's insignificant. You guys are really quiet. I'm not a comedian. I'm not funny. I think I'm funny, but nobody else is. So you guys are really quiet and you're not asking questions. You're just kind of giving me a blank stare, and I don't know what to think of that. Anyway, let's keep going. We have the F statistic. One variable that's related to that statistic is a t-statistic. This is a t-statistic that describes the difference between the estimated coefficient and some hypothesized value of standardized units. or by the number of standard deviations of the coefficient. So we can think of what we just talked about, the F statistic, as a test whether all the coefficients jointly affect the dependent variable, right? This, on the other hand, the T statistic tells me where one coefficient or one variable affects the dependent variable. So if it's above the significance level, we say it's significant, below it's insignificant. So the way I do it is I take what I estimate for the coefficient minus some null, and 99.9% of the time, it's zero. The null on beta is zero. I've seen it once where it's 1. Other than that, it's always 0. I want to know whether the coefficient is statistically different from 0. I take that and I divide it by the standard error of the coefficient. Now the standard error is very similar to standard deviations, except we use degrees of freedom, n minus k, in calculating it. Okay. For both the T statistic, I have a choice. I can do a two-tailed test. That means I just want to know that my beta is different from 0, or I can do a one-tailed test. That means I just need to know that it's not 0 or negative if it's positive, or vice versa. It's not 0 or positive if my coefficient's negative. In other words, the two-tailed test, right, is just different from 0. A one-tailed test has direction. In general, a one-tailed test is harder, and when I say harder, the number that you have to get to for it to be statistically significant is bigger. Okay. Questions? Now, when I first took econometric classes, and actually all through the time I was a student, stepwise regressions were frowned upon. Right? It's an experimental method of independent variable selection based on the independent variable correlation. Right? So after picking the independent variables that should affect the dependent variable, a researcher can add and subtract variables to get a model with the best fit. In other words, with the best R squared, the best F statistic, the best T statistics. Right? In addition, I can change the functional form, both from linear to nonlinear, whatever it might be. Again, this should be done with variables that theoretically or logically affect the dependent variable. In general, most people did something like this. You'd start off with a theory, you test it, and then you'd add or subtract variables. What was frowned upon is just picking a bunch of variables and then adding or subtracting variables. But now, statisticians have made it more acceptable. Okay. Questions? Problems with regression models. The first one, and probably the biggest, is something known as multicollinearity. This is a situation where the independent variables are correlated with one another. Originally, regression analysis was done to estimate how soil or different soils, different fertilizers affected crops. And because of that, they could make sure that the independent variables, right, were not correlated with one another. That they were, I'm going to throw 2 words at you that you don't need to remember, that they were orthogonal. In other words, that means that they weren't correlated with one another. If you do the matrices, it just means it crosses, so they don't move together. But after they did this, people saw this and started applying it to social sciences, where you couldn't control the independent variables and make sure that they weren't related to one another. The problem with multicollinearity is that it makes it impossible to identify the degree to which individual independent variables affect the dependent variable. In other words, your betas are going to be biased. I might know the total effect that these variables have on my dependent variable, but those coefficients are going to be off, right? Because it might be the price of X or the price of Y affecting X more than the price of X. And those beta coefficients, right, might be off if the price of X and the price of Y are correlated. Okay. So as I said, it makes it impossible to identify the degree which individual independent variables affect the dependent variable. In general, it's very hard to get around. One way to do this is with a two-stage method, where you take one of the variables, you pull it out of the regression, and then you estimate that variable with the other independent variables, right? And then plug it into the regression, doing the statistical techniques and doing it. That's something you guys don't need to worry about. Just know that multicollinearity is a problem. Residual. What's a residual? Well, like I said, the difference, right? The standard error of the estimate was the difference of the sum of all the points and the line. A residual is just one of those differences, right? So the difference between the point and the line, right, is a residual. Now, those residuals are going to have problems, or can have problems. The first one is they can be heteroscedastic. I know that's a big word. All it means is the variance, right, of your residuals is not constant. In other words, through one part of the data set, it might be bigger than the other parts of the data set. That's the definition of heteroscedasticity. By the way, sometimes it's spelled with a C, depending on whether you're in England or the United States. So heteroscedasticity is non-constant variance in the distribution of residuals. The other problem we have with residuals is serial or autocorrelation. This is a bigger problem with time series data than it is with cross-sectional data, right? The residual in one data point is correlated with other regressions. This is usually only a problem with time series data, and therefore the data points that are correlated across time. So in other words, you might have the residuals, like for instance, if you're doing it by quarter, every third quarter, residuals are bigger. Or as you move on in time, the residuals get bigger. Or, right, every 2 years, right, residuals get bigger or smaller. Basically, in other words, you don't have constant residuals over time. Those residuals change, and it's usually one residual is correlated with another residual in your time series data, or in your data set in general. The way we measure that is with something known as a Durbin-Watson statistic, right? It's a measure of the extent of serial correlation. The value needs to be as close to 2 as possible when you do this. And that's just the way they set it up. They really could have done it where it should have been 0 or something, but they just did 2. So basically, if it's close to 2, and again, you'll have a distribution, you can go to the table or the computer can spit it out. They'll tell you if it's significant or not. Right? So if it's close to 2, statistically indifferent from 2, then you don't have 0 correlation. If it's statistically different from 2, then you have serial correlation. Questions? Okay, so here's an example of a demand function, right? I have the demand for X is equal to a constant 100 minus 2.1, the price of it times the price of X, Px, plus 1.6 times the price of Y, plus 1.2 times I, where I is income, plus 1.5 times A, where A is advertising expenditure. Okay. So if I increase advertising expenditure, I don't remember if I do this in thousands now. But let's say I increase advertising expenditure by 1. How much will that affect my demand for X? You want to tell it, you want to say it, I do. I know, no? Anybody else is just itching to get it out? Come on. Sorry?
The question again.
If I increase advertising expenditure by 1 unit, right? What happens to my demand for X? According to the issue. 1.5. Yeah, that's our coefficient. So it's basically a partial, right? I'm taking the partial of A, holding all of these fixed, right? And basically it, it changes the quantity of X by 1.5. How much of this, how much of the variation in the demand for X does this regression explain? It's a long day, you guys are glazing over on me. I'm sorry? 85%. There's somebody back there that's awake. Okay. 85%. Why is that? R squared. Our R squared is 0.85. That means 85% of the variation in our dependent variable, in this case Q of X, is explained by the regression. That means how much is not explained? 15%. Okay, and our F statistic is 1.53. Again, we'd have to go to the table or have the computer spit it out to know whether that's significant or not. But it's big enough to where it's probably significant, depending on how many degrees of freedom we have. Now, the standard errors of the coefficients are in parentheses. Now, if I wanted to do if I wanted to test whether a coefficient was significant or not, in this case, let's say significantly different from 0, right? Using our t-statistic, how would I do it? Did I go too fast? Did I know that you write it or whatever? Okay, let's pick a coefficient. Let's pick the coefficient on the price of X. What's the t-statistic to test whether the coefficient of P of X is significantly different from 0?
So we have to take a chart.
Actually, I just want the t-statistic for now. Once we get the t-statistic, we can do it.
So we would have 2.1.
Eh?
So we would have B minus B no, so that would be 2.1 minus 0 over 0.81 then?
Exactly.
Okay.
Help me out, guys. What's okay? He said the coefficient is 2.1. Yeah.
La ecuación que era B menos B nulo sobre standard error, pues el paréntesis es standard error. Entonces el nulo va a ser 0, pues 2.1, el precio de X, 2.1 menos 0, que es 2.9, sobre 0.81, que es el error. Entonces ya estás midiendo si es relevante o no te va a dar el número. Me recuerdo un poco la casa estadística del semestre pasado. Aunque sea.
Okay.
So then we
2.1 over 0.81 is how much? 2 point something, right? 2.6. Okay.
So how do we know then if it's relevant? What's our
Well,
gauge?
we'd have to, in general, we'd have to know first of all what the degrees of freedom are. We have to know how many observations minus K. What's K? K is 1, 2, 3, 4, 5. So N minus K, and then we go to the table. in general, as long as you have enough observations, basically, if your T statistic's over 2, it's significant at the 0.95 significance level. And so if you have like thousands and thousands of observations, right, 2.0 will probably get you a significant level close to 0.99. But if I gave you a test, I would tell you the significance level, blah, 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 or the cutoff, the critical value is this, 90%. So you just tell me if it's above or below. If it's above, significant, below. Okay. And of course, these are what I already told you. Quantity demanded for X, the price of X, the price of Y, income, and advertising expenditures. Okay. The next thing I want to talk about is something known as a p-value. A p-value is related to the t-statistic, but instead of getting the t-statistic and seeing where it falls, whether it's significant at a certain level, this will tell you at what level is significant or not, so it goes backwards. So the p-value is 0.005 for the coefficient of A. What that means is A is significant at 0.995 level of significance. Just that one minus that. This means the probability of t-statistic for the regression coefficient of A would be at least as large in absolute terms as it is in the case of, in fact, A has no effect on Q of X. The results. So now, let me go back and write regression on the board. So I have Q of X. ¿Es grande suficiente? Equal to 100 minus 2.1 px plus 1.6 py plus 3.2 I plus 1.5 A, and of course let's do all the standard deviations, standard error. Squared is okay. So now I want you to assume the following. Assume income is 5,000. Assume PY is 1,000. Assume advertising is 20. It's in thousands, but just write 20. Don't write 20,000, just write 20. If PX is 500, I want you to estimate or calculate the quantity demanded for the product. So use that formula over there, plug in all the variables, and just pull out your cell phone and calculate. Sorry, I'm sitting down, my knee's bothering me.
In this case, those are the coefficients, right? 500, 5,000.
The variables. So basically, I plug in 500 for P of X, I plug in 5,000 for I, 1,000 for P of Y, and 20 for A. And then I sum up all of those. I take 2.1 times 500 plus 1.6
Oh, exactly. Where's that PX? Okay, now I get it.
times 1,000. And don't forget the intercept, which is 100. By the way, I guess I should have told you, save all the numbers or write them down for I, A, and P of Y. Keep them because you're going to use the same ones again. We're just going to change P of X to get a demand curve. ¿Perdón? Quantity demanded, sí, pero eso es que necesitas calcular.
Like very traditional, so very.
Lo que tienes que preguntar es Q de X a la raíz.
Sí, no, yo sé.
En el caso de si ese río, ese cálculo es hay otro punto.
Acuérdate que el coeficiente de precio negativo.
Exacto.
¿Qué es eso?
Exacto. Una serie de datos que se le
Eso es lo que te pregunto, donde saco lo que cabe en el número de la pregunta es la que lo que es pequeño.
No, que desde los también
Okay,
ecuación de línea.
ahora,
Me imagino que se puede sacar de ahí, ¿verdad?
todo el mundo cogió 16,480. That's right. My bad. I was thinking it was wrong, but okay. 16,480.
Pero el error es que el 100 es negativo. El primer 100.
¿Es negativo?
Sí.
Oh, okay. I need to go back. So you're saying it's 380? Wait. 480. Okay. Oh, so I'm right. Okay. I thought you were telling me I was wrong. Sorry. I apologize. You're right. And I apologize if you guys. I apologize. Okay. Now what I'd like you to do is pick another price. Any price. If you did what I asked you and saved the numbers for 1.6 times TY, 2.2 times I, 1.5 times A, you can make P of X 0. You already have all the other numbers. Or you can pick any X, any price of X. Make it 750.
Are we just changing P of X?
All we're doing is changing P of X. Everything else stays the same. Necesitas cambiar. Entonces lo puedes cambiar en cualquier número. Bueno, como ya tienes esto, lo puedes hacer. Es más fácil.
Es una falta de respeto para los mortales.
Esos son los errores cambios. Ese es básicamente. No. The p-value, you write a p-value using it's sort of aggregation, but you read the field. So it's essentially an aggregation. So it's just how they. That I gave.
Ese nombre que está muy bien, pero sí es fácil.
Ah, bueno, es que te digo ahora cuánto nombre. That's it. This is it. Yo voy a elegir.
Entonces, te das cuenta que mientras más pequeño el precio, mientras más pequeño el precio, más ventas.
Ya tienes los números y los restos de los números. Espectacular. Más fácil.
Sí.
¿Qué número usaste? Era mucho más fácil usar cero.
Cuando le cero, es más.
Pero también más.
Era mucho más fácil usar.
Ah, perfecto. Pero comprende tus notas. ¿Para qué estás haciendo? Para derivar la figura de demanda.
Vamos a empezar con cáncer.
Esta demanda. Por supuesto, tengo más aquí.
Arquitectura, ingeniería,
Yo creo que es mejor creo que sí,
No sé si quieren otro, hay otro día.
creo que
Solamente necesito construir.
Bueno, no, porque te mata,
Plus, 1.6 times 1,000. Plus, 3.2 times 5. Plus 1.5 times 20.
eso es la culpa entonces. Entonces, habla de la
Eso te va a dar 16. Solamente yo quiero cambiar este crecimiento.
yo según el texto lo de la regresión, y estoy tratando
Ahora hace la calidad.
Lo he pasado.
It is what is called the intersection.
And in terms of what is it, is,
In other words, if all of those numbers were zero, if the price was zero, if the price of oil was zero, if income was zero, and advertising was zero, right? You demand negative 100. Now remember, this is a linear regression. Obviously, we're not going to demand negative 100, but that's what the line goes to, it goes past the intercept, where the price is zero, where all the rest are zero, everything's zero, sorry. And in that case, we pass the intercept at negative 100.
you always give up that value, or we have to calculate this.
In general, I'm not gonna ask you to do this.
Okay.
I'm gonna give you the numbers, I'm gonna give you an R squared, and then I'm just gonna ask you to do.
What determines the intercept?
What determines the intercept?
Yeah.
The regression.
That isn't for the.
Uh, I take this line, and I pick the smallest sum of all those errors, to get the standard error of the estimate, and that gives me that line. And wherever that line hits the intercept, all right, is where it is.
Oh, okay.
And this is, I mean, we can't do, this is a two-dimensional graph. Over here, we need a four-dimensional graph, which I can't do. I might be able to do a three-dimensional graph, but there's no way I can do a four-dimensional graph. So basically, the intercept, with all those other ones being zero, would pass at negative 100 with this regression line. Okay, so everybody got 16,480, or more people. Now, if I use price of zero, I get, which is the easiest because you already calculated all those other ones, 17,580. If I change price to 8,348, I get quantity of 0. Quantity of demand of 0. So I just did those two. I connect those dots, and I get a demand curve. What should the slope of this demand curve be? Yeah, well, actually, you can do it. What is the slope of, what's is the slope that this demand curve should have?
Negative 100?
I'm sorry?
Negative 100? Oh, wait, no.
Negative 2.1. Did I point at the 100?
Yeah.
My bad.
Okay.
Negative 2.1. That's the slope of this demand curve. So for every dollar price increase, demand decreases by 2.1. So now, I have the standard errors. I have the first thing I'm going to do is ask you to do something I've already done, or you've already done. What is the t-statistic for the coefficient of p of x, right, with the null hypothesis that the coefficient is not statistically different from 0. In other words, V null is equal to 0. You guys told me already, we did this already. It was 2.59.
2.59.
69?
59.
Oh, 59,
We're
okay.
really close to this.
All right, and now, I'd like you to do the same thing for I. What's the t-statistic, assuming V null is 0?
Can we see the how you got to the 2.59 before we go ahead and try to do the?
Sure.
Thank you.
Okay. So our t-statistic, actually, let me go back over here so you can see the. So in this case, B hat, right, is 2.1. B null is 0. And my standard error of regression is 8.1. So it's 2.1 divided by 0.81. Okay, now I'd like you guys to do the same thing for my coefficient on income. Again, I'm assuming, right, that it's different from 0, so therefore B null is 0. I'm sorry? It's going to be, yeah, 2.9, 2.8, somewhere around there. 3.2 divided by 1.1. I'm sorry? 88? Okay. So I'm just going to write the t-statistic of px and the t-statistic for I. So if my cutoff, and let's say the 99% level of significance was 2 or 1.995, are these coefficients significant or not?
Is the income coefficient? The income coefficient, right?
I'm sorry?
You're asking if both the income and price.
I'm asking if the coefficients are significant. You take them one at a time, right? If my cutoff at the, let's say the 99% level of significance, if that's 1.995, it's basically 2, right? Are these two coefficients significant?
They are.
They're both significant. They're both over, right? That cutoff. So that's how I determine if they're significant. if I go to the table, and I'm not going to the table, but I know it's more or less 2 if I have enough degrees of freedom, right? So if I have, let's say, thousands and thousands of degrees of freedom, then 2 will give me a 99% level of significance, and these are both above 2, so they're both significant. How about the coefficient? I'm sorry, the intercept. Would that be significant? Assuming the null, I'm sorry?
Is that what you're asking?
Yeah. You shouldn't even have to do the calculation, just look
Well,
at, you know,
actually, yeah,
more.
exactly.
Huh? It's not?
It's not,
Okay.
it's less than, let's see,
The t-intercept.
it's like negative 25, right?
I'm sorry, because I didn't go over this, this is why I chose this. I didn't do the calculation, but I know it's approximately 3.9.
But it's negative.
Yeah.
Sorry?
It's negative 3.9.
Thank you, it's negative 3.9. And that's very important, because I haven't told you that when we do the significance level, it's in absolute terms. So is this significant? Yes. I just want a big t-statistic, that's what I want. It doesn't matter if the coefficient's negative or positive.
I got a doubt. I already know, I can do the math. You can give me the numbers and I can substitute them. But in the formula, that's the demand formula. I want to know what exactly each number means. So from back to forth, the A, I know it means advertisement. So every time I increase my, so you will give me a number. That number in this case is A is 20. So let's say that's like a cost of or an investment of 20 in
Okay.
advertisement.
It's 1,000, but we're for the regression, I'm just using 20. So 20. Now, for every 1,000, that means for every, in the regression, every 1 increase in A,
Exactly.
right? So if I go from 20 to 21, the quantity demanded will increase
Yeah,
by
will increase.
1.5.
Okay.
So if I increase advertising by 1,000, right, my quantity demanded, in this case, 1 is quite demanded.
And the same for investment is 5,000. So for every $5,000 I invest,
Okay, it's not investment, it's income. But, okay, but you're right. So let's say I increase income from 5,000 to $5,001. My quantity demanded for X will increase by 3.2.
and the PY and PX is just the price of a product.
The price of X, right, its own price. Price of
Okay,
X.
versus.
Price of Y is another product.
Okay.
In this case, it's positive, so if this is positive, is this a substitute or a complement? P and Y. Substitute or complement? Substitute, okay, this is positive. Remember? I know, you guys don't remember this was 2 weeks ago. Okay, so in this case, if the price of Y increases by $1, the demand for X increases by 1.6. Did I answer your question?
Yeah. Oh, and the 100, what exactly does the 100 mean there?
The 100 intercepts, in other words, theoretically, if all of these things were 0, if advertising is 0, income 0, all of them 0, the demand for this product, demand for X would be negative 100. And that's because it's linear, right? You gotta fit the line, and where the line is gonna hit, it's gonna be negative. Questions? Okay. Oh. Okay, the next question is, how well does the data fit? I'm sorry, how well does regression fit the data?
Okay, can we go over what the bottom numbers are in the parentheses? Is that gonna be given in the exam? How do we get those?
They'll be given, those are the standard error of the coefficients. They're essentially the standard deviation, right? But we divide them a little differently. In other words, we're dividing by degrees of freedom instead of by n-1 what we use for the standard deviations. Here we n-k. So it's basically the variation of that coefficient, right? So if you know what a standard deviation is, standard error is very similar. So basically the variation of the coefficient, the standard error. And yes, so I'm not, for this class, you're never going to calculate that. You're going to be given that. Okay. So, how long does the regression fit the data? How much of the variation in the data does the regression capture? I'm sorry? 85%, perfect. And we know that because our square is 0.85. So it's pretty good, and our F statistic, 5.3, which is a decent F statistic. I don't know what the cutoff is because I don't know what my degrees of freedom are. I don't know how much data I have. So now, I just want to show you a couple of statistical outputs. The first one is in Minitab. Minitab is produced at UPenn, and the authors are from UPenn, or at least the main author is from UPenn, so we use Minitab. And here we have a regression, right? C1 is equal to 5.3 plus 1.76 C2 minus 0.35 to C3. So let's do just one more quick T statistic or T exercise. If the standard error of C3 is 0.07, let's go 0.076. What's the T statistic for C3? Those of you who are so let me just do the C3. Negative 0.352 C3, right? And the standard error, which this package calls the standard deviation. What would my C statistic for C3 be?
Negative 4.9.
Negative 4.9. And for some, 9.8, right? And for those of you who are smart and just looked at the output, it will tell you that.
Oh, yeah.
So the T ratio is right here, negative 4.98, right? So I have my coefficients, I have my standard errors, I have my T, and then I have my P values, which mean all of the P values are fairly small, which means that all of these independent variables are significant, right? And very low levels of, very high levels of significance. 0.999, 0.999, 0.998. What's the R squared? What's that? 99.4 is right here. So this regression explains 99.4% of the variation in C1. What's the F statistic?
It's the what?
I'll give you a hint. I passed by it just now. 5.25. Right here, 5.2572, that's F statistic. And the p-value for the F statistic, that would just give you the cutoff, is 0.000, so 0.999, level of significance for the F statistic. So this is a regression that, excuse me, that explains a lot of the variation in the dependent variable. Now, the next thing I'm gonna show you is the same regression, but with a different statistical package. This is known as SAS, Statistical Analysis Software. This is probably the most common statistical package used by statisticians. Right? SPSS is another one. They're used by a lot of social sciences. It's a little less complicated than SAS. But again, we have all our coefficients. We have our standard errors, which is actually the true name. We have our t-statistics, and we have our p-values. And then we have our p-value for f, and we have our r-squared and adjusted r-squared. Questions?
I imagine there are websites like where you can create these sort of setups, or is it a program?
No.
It looks
You know,
like
now there probably are websites where you can go ahead and input data and get a regression.
not just the regression, I mean that format for presentation of the statistical data.
No, this is copy and pasted right out of the software, right out of the software.
Okay, yeah, so you need a software, okay.
Okay, questions? All right, that's it. I will see you guys next Wednesday. Have a good weekend. Today's Monday? Oh, wow.
Yeah.
It can't be Monday.
It's gonna be wrong.
I will see you guys Monday. Have a good week.
El tiempo